Hello everyone, my name is Mustafa and I am PhD candidate from University of Campinas, Brazil. My area of research is quality of service and quality of experience in video traffic. In IEEE Globicom demo sessions, we provide two of our research work as a demos. In the first demo, we provide a framework for the evaluation of QoS and QoE using 4G and 5G use cases. And in the second demo, we provide a framework for the collection of YouTube quality of experience KPI with channel level matrices. Okay, now I will talk about a framework for quality of service and quality of experience assessment of encrypted video traffic with 4G and 5G open datasets. 5G has been rolling out to deliver high data speeds, low latency, and support more users as compared to 4G, where comes the role of edge computing. Edge computing is to reduce latency, provide real-time response, reduce congestion in the network, and better performance to video users using various machine learning techniques. So it has become a critical issue for mobile network operators to manage exponentially increasing video traffic where deep packet inspection no longer provide information such as quality of service KPIs. So what is the motivation behind this work? TLS encryption establishes a more secure and private connection where classic deep packet inspection techniques no longer provide valuable information. And due to the limited information available to inspect video flows, it is difficult to find lightweight quality of service patterns affecting the video quality. The exponentially increasing video traffic demand poses many challenges for the mobile network operators to provide maximum quality of service resource for higher quality of experience. And the traditional approaches consider YouTube as a baseline to derive quality of service features from an encrypted stream along with chunk level statistics. And we all know that where YouTube delivery mechanism vary over time. So what is the problem? Taking subjective feedback at the end of every video session is not ideal from mobile network operators perspective. More subjective feedback is affected by various other factors such as age, gender, mood, and type. And find a QoS relation to QoE of video traffic from available features, which is packet time and packet size, and then an intelligent solution to passively monitor network condition and help mobile network operators to make decisions for better resource utilization. So what is the solution for the problem? Using the interpacket gap, IPGs are the main metric that provide maximum information gain to estimate quality of experience. We provide a solution to extract quality of service feature in the form of window. Window is of any time, for instance 1, 2, 3, 4, and 5. Then use IPG of a window to derive more features such as exponentially weighted moving average, double exponentially weighted moving average, and cumulative sums. Then intelligent QE prediction solution from these lightweight quality of service matrices is ideal for mobile network operators to take smart decisions. So in the solution, we have to keep an eye on interpacket gap. IPG is a novel metric that provides maximum information gain in traffic, followed by these QS feature that we derive from IPG. These are EMA, then DEMA, and QSUM. Usually, these metrics are technical indicators used to identify a potential uptrend or downtrend in a time series data. We use these matrices to find where the continuity of data packets change from the mean value. So instead of finding a chunk level statistics, use window-based QoS feature instruction method, which is efficient, lightweight in terms of complexity and processes. More, a window is flexible in the framework. A window could be seconds, half of the video session, or a complete session. So this algorithm explains the whole the QoS feature extraction method of a 1 second window. So we have 28 QoS features that we derive this from 1 second window. So this 1 second, this window can be of 2 second, 3 second, 4 second, or up to half session or up to a full session. So here I will explain 1 second window QoS features, which are packet size distribution. These are 9 features. Then throughput distribution, 9 features. Then we have throughput, total packets, packet size greater than 100 bytes by ignoring control packets, and then IPG average of a window and IPG average of window of size, packet size greater than 100 byte. Standard deviation of packet size greater than 100. IPG standard deviation, IPG standard deviation of packets whose size greater than 100 byte, and then inter-arrival time. Then we have an interpacket gap of all of a window, and then we forward these interpacket gap to our functions that derive these three matrices EMA, DEMA, and QSUM. So we have these 3 QoS shift matches of 1 second and 28 QoS feature that we have before, and then we have 31 QoS feature that we derived from a 1 second window. So we use Mininet network emulator, a video caddy video server, and GoDash video player, and TCP dump to network packet sniffer, and then scripts to run the whole scenarios, and the bash scripts to emulate 4G and 5G bandwidth traces, and then Python scripts that process window-based QoS feature from network traces. So we have a caddy web server here, then two OBS switches connected to each other, and at this point we use link utilization based on several network traces, 4G and 5G traces. Then our probing scheme here to capture the network traffic and the video log at this point. After pre-processing of packets, we have network level QoS features, and then we also have objective quality experience KPI per segment KPIs. And then we provide data analysis in the form of interactive notebooks and the QE prediction, which you can use quality of service patterns to predict quality experience KPIs. Now we'll talk about the results that we generated from the static use cases. These static use cases of the 4G and 5G traces, and we show the results for the conventional throughput based ABS algorithm, then elastic, it's a hybrid base, and the buffered base. We also show three quality of experience model P.1203, clay, and MNO. So we can see that conventional in 4G and 5G experience a sort of quality experience. Elastic is slightly better as compared to 4G in 5G, and BPA in 5G has much better quality experience as compared to 4G. We can also see the 5G experience better quality experience P.1203 score. We can see that 80% is remaining in 4.5, but in case of 4G it's remaining less quality experience, which is near to 4. Okay, if now we talk about the 4G and 5G resolutions, we can see in 4G 56% of time it's remain in high resolution, but there are a lot of quality shifts between other resolution, and the percentage is much higher as compared to 5G. We can see that 87% it's remain in high resolution and bitrate, but very few remains in other resolution, but their percentage is less. 4G also experience more stalling event as compared to 5G. We can see there are a lot of stalling events in 4G. Now I'll talk about the result of use cases with real interruptions. When I talk about real interruption, these are the use cases that we generated from running YouTube streaming sessions, and we experienced massive stalling events there. So we select two use cases, one for the 4G and one for the 5G, and we show two quality of service KPI, which is throughput, and EMA. EMA is derived from interpacket gap, and we can see the throughput at this point is less for the first 50 segments here, because we have less resources at this point, and we can also see that a lot of peaks at this point, which causing less quality of experience at this point, and that also experience stalling event at this point. So this is 4G TCP, and we show the correlation of the objective quality of objective QE stall and P.1203 for the buffered base algorithm of 1 second window. So for the other algorithm, elastic and conventional, we experience same sort of patterns. We see at this point few peaks, and there is less throughput at this point, which is causing less quality experience at this point and stalling events. And if we talk about conventional, we see peaks at here and less throughput here, causing less quality experience model P.1203 here and stalling events at this point. So if we talk about 5G quality of service to quality of experience feature correlation, we experience for BBA, elastic, and conventional same sort of patterns. We see few peaks of EMA values at this point here, and also peaks, and here we have few peaks, but they are causing less quality experience at this point, less quality experience at this point, and less quality experience at this point, and are experiencing stalls. So what is the final consideration of this framework? We accessing QoS for the video streaming for TLS encryption is challenging for mobile network operators for better service level agreement and root cause analysis to take effective measure for better quality experience. Moreover, the classic way of taking subjective feedback after the session is sometimes not efficient, where we provide a lightweight framework to better understand quality of experience and quality of service relation by various network conditions to take intelligent decisions by mobile network operators. Moreover, the framework is flexible for various type of settings, protocols, TCP/K, ABS, hybrid, throughput, buffer-based, and real 4G and 5G traces. You can download framework from our GitHub repo, and video instruction how to use framework is also available in the framework. The video demonstration how to use the framework is also available at this link, and the dataset generated during the experimental phase of the framework using two videos, Sciental and Tears of Steel, using protocol TCP/K with 1 second window for QoS feature extraction is also available at these links. Now we'll give you a live demo of how the framework will work. Thank you. The framework is available at this link, and you can make your own setup, or you can download a VM with all the scripts and dependency. To make your own setups, you need Mininet Wi-Fi, Go-Bed, and a caddy web server. So what are the steps? So first you need to install Mininet. The next step you need to install Go-Bed. You need a video. You can download video from this link. You will find 2, 4, 6, 8, and 10 second segment size. But in the we select 2 second segment for experimentations. Once you download the video, you need to move to this directory in the Ubuntu. Then you need to run run.py, where different type of parameter you need to set. I will show you this in a few minutes. And then there is a topology. Each experiment generate one PCAP and one Go-logs, and to extract QoS features from the PCAP, download scripts from this link. So now I will explain run.py and different type of parameters you need to start to run experiments. So this run.py is available in downloads, and then Go-bed, and here is run.py. So run.py you need to set the 5G environment, number of hosts competing for the video streaming, and different type of ABS algorithms. So this is a list. You can also provide more algorithms here. So I'm passing two ABS algorithm this time for the experiments. Then these are the use cases. So these are also use cases, and this is also an list. And then there's a protocol cake and the server type, and then how many times you need to run this experiment. So I'm running this experiment just for one time. So just go in the framework directory, open the terminal, and just run the file run.py. Okay, now it's running an experiments with it's 5G, and it's taking a trace 5G RC1, and number of hosts are 1, and the protocol is cake, and the algorithm was elastic. So once you run this experiments, it will generate one PCAP and one Go-log file in download in Go-directory here. So you can see this is running an experiment, and it is elastic with quick protocol, and it is using 5G trace 5G RC1 use case. So here is the PCAP file, and here is the logs. So now in the log file, what is inside the log file, I explain here. It is also, the example is also available on the GitHub repo. So this is the log file will be generated. So you have the per segment logs for the arrival time, delivery time, and the stalls, and the representation rate, delivery rate, actual rate, what is the byte size, buffer level, algorithm for the experiment is running is elastic, but this is an example of PPA. Then what is the segment duration? So I select 2 second segment. What was the codec? And this is the resolutions for 320 into 180, and you can see that it is slight. Then after some time it start increasing with the high resolutions. What were the frame per second? What is the play positions, RTT of the applications, and then the protocol, and then these are the 5 QE model that provided by the Go-logs. So now the QoS features that we extracted from the PCAP, then the PCAP is from this PCAP that is generated from after each experiment. So we have okay, so for the experiments, so as I said, this is the experiment 1, because we are running the experiment just for one time. What was the video? So what is the window size? So this is the window size. So this QoS features of the 1 second window. What is the type? It's a 4G type, but the experiment is running with the 5G. What is the algorithm, and what the QoS feature from time 0 to time 1? So there we have inter-arrival time data packets. The inter-arrival time of data packets of packets greater than 100 bytes. Then average time between data packets. Then average time between data packets of packets whose size is GT represents here greater than 100 bytes. Then we have throughput. Then we have total packets. Total packets for GT 100. Then standard deviations of GT and greater than 100, packet size 100 byte. Then we have these shifts metric, USM, EMA, and DEMA. Then we have packet size distribution, which is 10, 20, 30 into 90 percentile. And next we have throughput distribution starting from this 10 10 percentile of throughput to 90 percentile of throughput here. So once the experiment will finish, the script will automatically terminate. Okay, now I'm going to terminate it, the experiment. So you will find an experiment with one go dash log and one pcap file. So in the next you need to run the Python script that will fetch this window-based QoS feature extractions from the pcap, and you can select from 1 to 5 or up to your needs up to 10 seconds or maybe half sessions or the full sessions, and you have per segment QE logs of the experiments at this point. Okay, this is in a demo of the framework, and it is flexible for changing many parameters and settings that I explained you before. For example, you can add more ABS algorithms. For example, if you can also add logistic, and this is also a buffer based algorithm. You can also choose elastic. This is a hybrid, and then you have multiple, you can run on multiple scenarios. For instance, I'm running here two use cases. Then you have protocol cake, and if you want to run with TCP, you can run TCP. And there is a server type, and if you want to run the experiment for more than mm, two experiments, then you can select two. Then the first experiment will be with one one indicator, and second will be with the two. And if you are running experiment with 4G, you just need to pass here in 4G, and also you need to pass the traces to run. Okay, thank you very much for this demo and for my presentations. I'm open to take any questions from you. You can send me an email. Thank you very much.